Hello students, in the previous class we discussed about the series combination of the capacitors and the expression for the effective or equivalent capacitance Cs is C1 into C2 divided by C1 plus of C2. This is what the expression we get. Today's class will talk about the another combination of the capacitors, that is parallel combination of the capacitors. Two or more capacitors are said to be in parallel only if they are connected to the one common point. Only if they are connected to the one common point such that potential difference across each capacitor is same. Potential difference across each capacitor is same and total charge is the algebraic sum of the individual charges stored across each capacitor. In series combination we have seen that two or more capacitors are said to be in series only if they are connected end to end such that charge on each capacitor is same and total potential difference across the combination is the sum of the potential differences across each capacitors. Here in parallel combination, potential difference across each capacitor is same and total charge on the system is the algebraic sum of the charges stored in each capacitors. Alright, so let us see here the parallel combination of the capacitors. Say that this is the one capacitor, this is one more capacitor, I will call it C1, C2. They are connected to the one common point. This C1 and C2 are connected to the one common point. I call them as these two capacitors are connected in parallel. Like this, we can connect the parallel combination of the capacitors here. Right? So these three capacitors are connected in parallel combinations. Alright, so all the two or more capacitors are said to be in parallel only if they are connected to the one common point. Look at this, C1, C2 and C3 are connected to the common points. All three are connected to the common point. So we can call them as the parallel combination of the capacitors. Here potential difference across each capacitor is same, charge across each capacitor is sum of the individual charges. Right? So we will see here, we will find the effective capacitance or equivalent capacitance for the parallel combination now. Right? So before that I write here two or more capacitors, two or more capacitors are said to be in parallel, if they are connected to one common point such that potential difference across the combination is same and the total charge is the algebraic sum of charges stored in each capacitor, right? So two or more capacitors are said to be in parallel only if they are connected to one common point, such that potential difference across the combination is same and the total charge in the system is the algebraic sum of charges stored in each capacitor. Then only we can say that it is a parallel combination, right? So I'll draw here capacitors are connected in parallel combination. This is one capacitor, this is one more capacitor, so I will call it as a C1, it is C2. They are connected to the external source. See that V, that is connected to the potential difference or battery. So potential difference across each capacitor is same, charge is different now, so it is charge on capacitor C1 is Q1, charge on capacitor C2 is Q2, right? So in parallel combination, total charge Q is nothing but the Q1 plus of Q2, as the definition says here. The total charge is the algebraic sum of the charges stored across each capacitors. But we know that C is equal to Q divided by V. Therefore, Q is nothing but the C into V. So what I can write now, Q is equal to Q1 is nothing but what? C1 into V plus C2 into V, because V is same at each capacitor. Therefore, Q can be write C1 plus of C2 into the bracket V, right? V is common here, so say it is equation number 1. If Cp is the equivalent capacitor, then if Cp is equivalent capacitor, then from this relation we can write Q is equal to Cp into V. Q is equal to Cp into V. Say it is equation number 2. So from equation 1 and 2, we can write Cp into V, which is equal to C1 plus of C2 into the bracket. So this V get cancelled. What remains here? Cp is equal to C1 plus of C2. Right? So this is the equivalent capacitance of two capacitors connected in parallel combination. Cp is equal to C1 plus of C2. As I said in the last class, equivalent capacitor is a single capacitor which produces the same effect as produced by the combination. Whatever the effect is produced by this combination, the same effect can be produced by the single capacitor, that is called the equivalent capacitor. Right? So this is the final expression for the equivalent capacitance connected in the parallel combinations. So remember one thing here, in series combination we get Cs is equal to C1 into C2 divided by C1 plus of C2, right. Here equivalent capacitance in series combination is always lesser than the individual values given, right. If suppose that C1 is given 5 microfarad and C2 is 10 microfarad, then Cs will be, or Cs will always less than these two. Cs is always less than these two. If I substitute the values of 5 and 10 here, I get what? 50 by 15. So it is around something 3.5. So Cs is always less than the individual capacitance given, right, while Cp is always have the greater value than that of the individual capacitance. Effective capacitance in parallel combination is always have the higher values than the individual values given, and effective capacitance in series is always have lesser value than the given individual values, right. Same example I can give here in the Cp. If C1 is 5 and C2 is equal to 10, then Cp must be equal to 15. So it is always greater than the individual values. Okay, so this is all about the parallel combination of the capacitor. In the next video we will talk about the energy stored in the capacitors.